Hi everyone, so it's very nice to see you again. This is a presentation for E542, the lab file, fast reliable file transfer with custom TCP IP. I am Boyang XIAO and the rest of my two teammates are Yixing WU and Donghao ZHAO. So there are three parts in this time's presentation. The first part is the file transfer performances with no modification to the kernel. And the second part is the kernel modifications and compilations. And the third part is the file transfer performances with the modified kernel. So let's dig into our presentation.
Now I'm going to transfer 1 gigabit file by using the SCP protocol and test the throughput of this transmission. As you can see, I set the TBF rate as 100 megabits and 40 milliseconds delay and 5% drop loss in this link. And the final result is the 991 kilobytes per second.
Hi, this is Donghao ZHAO. In this presentation, I will show you how did we compile the kernel and how did we modify the TCP stacks. The first part is to change the disk size of our AWS instance because the compiling needs a lot of space. To do that, we need to go to the AWS instances page and select the instance. Then select the storage tag and click into the volume ID. Then click the Modify button in the top right. In here, we give the desired space that we want, say 30 gigabyte, then click Modify button. So next, we need to restart the instance. After the restart, the disk space of the instance will be expanded to the desired size. We can check this by using df-h command. The next thing we need to do is to create the swap space in our hard disk. To do that, log into the instance through SSH. We first check the current swap space by this command, and here you can see the swap space was 0. Then we create a file that will be used for swap by this command, and give the file the correct permission. Then we use make swap utility to set up the file as Linux swap area by using this command. Then we enable the swap by this command. Next, we would like to make the configuration permanent. So we modify this file and append an entry into this file, which is this entry. And after all of this, we check the swap space by using this command and this command. Now you can see that the swap space is 1 gigabyte compared with 0 in the beginning. Now we would like to download the source code of the Linux kernel. First, we install git by this command. To doing that, we need to configure git to use low memory by executing these commands. After these, we can start to clone the kernel but the instance takes too long to compile the kernel. So we will proceed the compilation process on the virtual machine in VirtualBox. So here I have set up a virtual machine that has 8 CPU assigned, and we will download the source code by doing git command on the virtual machine here. The cloning process takes several minutes to finish. After it is finished, we will have a folder named Bionic in the current path, which means that we have successfully downloaded the source code of the kernel. After this, we are going to build the kernel. Before doing that, we have to update the source list file by using this command, and we'll achieve this by uncommenting all lines started with dbsrc. After doing this, we will perform the sudo apt-get update to refresh the source list. Then we need to check the image version of the AWS instance that we created by doing this on the AWS instance using this command uname -a, and we can see here the kernel that the AWS instance is using is this 5401084, and it is built on August 14. Then we make sure the source code that we cloned have the exact same version by doing git tag with AWS. And we search for that. Here, we can see that we have the similar version here. So after this, we will install the corresponding build tools by performing these commands. These two commands. And after waiting for a long time of the installation, next we are going to switch to the branch that is corresponding to the kernel version by using git checkout command. After this, we will generate the configure file by doing this command sudo make old configure. Next, we need to do some modification of the .configure file by sudo Boyang configure. And here we need to search for trusted keys equals to this. Okay, so we need to modify two things here. The first is this. We need to it has its origin value, but we need to set it to empty, which is this. And also for this value, we also need to set it to empty. And after this, we also need to install another package, which which is this package. And after doing this, we can compile the kernel using this command, sudo make. I have 8 CPU assigned, so I will dash J8 here, bin that package. So if I perform this command, the compilation process will begin, and the whole compilation will need like 30 minutes on my computer. After the compilation finished, the output file will be located here. I actually have 6 files. If we have 6 files in here, then which means that the compilation is successfully done. Once we have compiled the kernel, we will upload the output files using SCP to the AWS instance by this script. Then, in AWS, we will check that the new kernel files that we just uploaded are here. Then we install the kernel by doing this command. And after the installation, we first check the boot library. The boot is here. We need to make sure that the new kernel files have been installed. Here we can see the new kernel files. Then we need to run the command sudo update grub to check which grub file is the operating system currently using, which is this command. Actually, the Ubuntu 18.04 no longer use the legacy grub, so we only need to modify the grub CFG file. And we do this by vi boot grub.cfg. And in this file, we will need to modify to check actually the boot option just above the first advanced item, which is here, which is these two. We need to check that these two files are the new kernel files. We can see that the files have 195 in its file name, so they are correct. And finally, we just need to reboot the instance. And after the reboot, we use the uname-a command to check the kernel version. uname-a. And we can see that the current kernel version is the new kernel version, and the compilation time is September 24, which is the kernel that I just compiled. Until now, we have correctly installed the new kernel. Alright, here I will explain the changes that we made for the TCP stacks. As you can see here, we summarize the changes to a form. It has the file name, line, modification, and origin column to illustrate the details about the modification, and has a purpose column that shows the reason why we made these changes. To prove that we changed the code according to the form is easy. We just navigate to the exact line of the file, and what we changed will show up. Then we just repeat this process. So I will not go navigate to all the lines of all these files. And instead, I would like to deliver some insights about why we changed these and with respect to the paper. So the first thing that we did is to expand the TCP window, actually doubled it, and also doubled the scaling parameter to match the expansion of the window so that the TCP have the potential to send more data. Then in the next sector, previously the TCP will trigger the fast retransmit after receiving 3 duplicated acknowledgements. But now we change this to 1 so that only 1 duplicated acknowledgement will trigger the fast retransmission. This is done because the network topology that we are using is very easy. So the packet should be able to arrive in order. And next, we changed this synchronization packet retransmission retries to 5 according to the paper mentioned here. It says that about 3% to reject a connection for those that abort a connection after 5 consecutive tries. So we change this value to 5. Next, because the HZ equals to 1024 and the current round trip time is 200 milliseconds, so we changed the retransmission timeout range to around 100 milliseconds to 600 milliseconds to trigger the retransmission faster. In this case, if the retransmission timeout, which is RTO interval, is set to around 100 milliseconds, then for each packet, TCP will transmit the same packet at least twice until it is acknowledged. And we also changed the transmission timeout to around 200 milliseconds to match the round trip time that is 200 milliseconds. Actually, a little greater than that. Finally, for this file, we enabled the Linabell algorithm to reduce the number of packets that need to be sent over the network. And then because the high congestion avoidance mechanism is suitable for high latency, high loss rate network, we choose to modify this file. Basically, we reduce the send window from 2 to 1 and the maximum window allowed for the network to this value, and change the send window to the maximum window allowed to bypass the sophisticated calculation of the high send window. Then for the congestion control file, we configured the window in the slow start phase and in the congestion avoidance phase all to the maximum window allowed. So this removed the exponential backoff and make the send window a constant. And finally, for the TCP.C, we changed the send window from 2 to the initial congestion window in the case that the connection is disconnected. Also, we removed the exponential waiting time so that every packet that is lost will be treated equally. In the end, we changed the maximum send window to the initial window so that it won't reach infinity in some cases. These are the changes that we made to calibrate the network. When we're done with this change, just replace the files in the source folder, then recompile the kernel, and then upload the kernel to the AWS instance and install it. Then the modification will take effect. Also, we need to change the congestion avoidance mechanism that the operating system selected by some command. So much for the kernel compilation and the TCP stack modification.
And then let's begin our part 3. So as Donghao has said, he has already got all of the Modifiy kernel and he has sent all the kernels to my instances on AWS. So let's firstly begin with the installing all of these Modifiy kernels to the instances on AWS. Firstly, let's log in to all of the instances with the SSH. As you can see, this window is the router, the VYOS, and this window is the client machine, and this one is the server. So I have already got the instances on my virtual machines. The folder name is kernel build modify. The client got one, and the server also got one. Yeah, let's see in this folder there are several files. You can see all of the red files are actually the installation packs for the Modifiy kernel, and let's just install them to our instances. Use the command here, and we do the same thing on the server. And we just have to wait until all of the installations to finish, and we can proceed to the next step. After a few minutes waiting, we can see that both the client and the server got their new Modifiy kernels installed in their operating systems. So there are no errors in the process of the installations, and we can then configure the instances to reboot with the new Modifiy kernels. Let's first go into the root, and we check this file, the grub config file. And as the PDF said, we find out the keyword advanced. And you can see that on the lines above the advanced keywords, the kernel has already been switched into the 5.4.195 plus. And this is the same version we build our new Modifiy kernels. So we can say that if we reboot the system will reboot with the new kernel. So let's close this file, exit, and we reboot it. Sorry, we reboot it, and the machine is rebooted, and we do the same thing to the server. Because the file has already been configured to launch with the new Modifiy kernel, so we just reboot it directly. And then we just have to wait until the two instances to launch again. So after a few minutes waiting, we can see that our server and clients are launched again. And before our testing, let me briefly elaborate the topological relationship between these three instances. So we can see from the client side, the client's interface 0 is connected to the subnet 2, and the server side, the interface 0 is connected to the subnet 1. And from our router side, we can see that the router has three interfaces. The interface 1 are connected to the SSH, and the 0 is connected to the subnet 1, which belongs to the server side, and the interface 2 is connected to the subnet 2, which belongs to the client side. So let's firstly add in bandwidth limitations to both of the interfaces on the router side. Firstly, the interface 0 and then the interface 2. And let's use the iperf3 to test if our limitation is valid. Firstly, let's launch the iperf3 on the server side, and then let's use this command to test the throughput of the TCP transfer. So we can see from the results returned by the iperf3, the throughput of this link approximately 100 Mbits per second. So our bandwidth limitations are valid actually. And then the next step is that we add a delay and the packet loss to both the interfaces on the router side. So we can see that both interface has a 100 millisecond delay and packet loss rate at 20%. So let's use the pin to test if our limitations are valid. Let's pin the server from the client side. 1.179. Okay, let's just pin 5 packets, and we can see that the delay in these links are 200 milliseconds, which is as we require for this testing. And for the packet loss, let's use the iperf, the UDP mode to test the packet loss in these networks. iperf 3, and we use the command here. Okay, so we can see that the packet loss are approximately 20%. So it's also as required for this testing. And then we can begin our test. So as you can see from the previous part, when we are modifying our kernel, we use a new TCP congestion control mode named Hybla. So when we are applying this new mode to our new kernel, we have to open it up in the configuration file. So we have to do this in this way. So we change the configuration of the root, and we enter this file. We change the mode to the Hybla, and we save it. We exit the root, and we do the same thing for the server. The root, change the congestion control mode to Hybla. We save it, and our mode has already been changed to the mode we modified. And then we can go to the test folder, which will be holding off the testing for this lab. And firstly, we made a data file and the size to set to be sorry about that. The size we set to be 1 gigabyte. Yeah. We wait a second until the data assignment to be finished. And then we can transfer our file from the client side to the server side using the command here. And let's begin the transfer. So we can see from the few seconds of the transfer process that the transfer rate is actually much better than the unmodified kernel, because if we use the unmodified one, the rate can be just begin from the several, I think, less than 100 k bytes per second. So with the modified kernel, we can see that the rate is much higher. And but because our latency and the packet loss is so high, so the rate can be fluctuating. So if we want to see the whole throughput of this 1 GB file transfer, we can wait until all of the transfer is finished and we can see the whole throughput. And our file transfer is finished here. So the throughput, let's do a little bit math. Let's change this to Mbps. We multiply it by 8 and divide it by... And we can see that the final throughput for our modified kernel is the 5.7 Mbps. So that is much better than the unmodified kernel. So we have also done the same kind of testing on the different network conditions, and the results are listed in this chart. So you can see from the chart that we range the delay from the 0 to 200 millisecond, and we also range the loss rate from 0 to 25%. And the SCP throughputs are listed here. So you can see that when the network conditions is very good, like there is no delay or no loss rate, the SCP can fulfill the whole bandwidth, like 100 Mbps. But when the network condition is very bad, like the delay is very high and the loss rate is also very high, our modified kernel can still guarantee that the SCP throughput is more than 5 Mbps, which is a very satisfying result, especially when we compare it to the unmodified kernel, like what is shown in this figure. So the figure on the left is the unmodified kernel results. You can see from this figure that when the network conditions is very bad, like the delay is very high and the loss rate is also very high, the unmodified kernel can have nearly zero throughput, which means that we can't transfer anything under these bad network conditions. But the figure on the right is our modified kernels, and you can see that no matter how bad the network condition is, our modified kernel can still guarantee that the throughput is more than 5 or more Mbps. So it can show that our modifications to the kernel is valid and is very effective. And I think that's all the analysis for this part of the lab. Well, that'll be all for our Lab 5. So if you have any concerns or questions, please feel free to contact us. So thank you so much for watching our presentation. Bye.